Okay, I think we're going to start the third keynote presentation now, and people will start joining as we go. So for our third keynote presentation, we have Dr. Panagiotis Kouvaros. He is the principal data research scientist at Safe Intelligence, and the work primarily focuses the development of formal methods for assessing safety and robustness of AI systems. So without further ado, start.
Thank you, Nikki. Thanks, everyone. It is my pleasure to be here. So in this talk, I will focus on neural network robustness. What is the issue? Why it is important? And how formal verification can help to address the issue. I will in particular talk about the main formal verification methods. I will give a brief overview of how they work and outline their disadvantages and advantages. So to start things off, let's assume that we train a neural network model and we tested it on lots and lots of data. And we found that the model performs really well. Now, irrespective of how many data points we used and irrespective of the testing scheme that we use, we're always testing the model on a finite approximation of an infinite environment. Right? So if we zoom in into a test point, we'll see that there is a whole area of test points that we did not consider. And this is important because if we move a data point in the input domain even slightly, what we will often see is that the outcome of the model changes. And this is very problematic in safety-critical applications because what it means is that the model will not be robust with slight environment changes. To give some concrete examples, in a runway detection model, we would like the model to be robust to different lighting conditions. In a credit default model or a non-application model, we would like the model to be robust to minor changes in the income. And formal verification tries to establish this robustness by not simply checking test points, but by checking these areas of input space around test points. So what in particular a neural network verifier does in the computer vision domain is that it takes as input an image, and it takes a dense area of perturbations around that image. This could be photometric adjustments, this could be geometric transformations, or it could be white noise. And then it outputs robust if the given model has the same outcome for every one of those perturbations. Otherwise, it gives a perturbation which violates robustness. So I will now talk about the main formal verification approaches, and I will focus on ReLU networks. These are the basis formal verification methods which can be extended to deal with other activation functions as well. A quick reminder on the ReLU activation function. This is a piecewise linear function. When the input is below 0, it outputs 0. When the input is above 0, it outputs the input. If we have some bounds, a lower and an upper bound on the input to the function, then we say that a ReLU is stable if it operates only in one of the linear segments. So if the lower bound is above 0 or the upper bound is below 0. Okay, with this, I will start discussing the main verification methods, and they all use the concept of bound propagation. So here we start with the dense area in the input being an infinity normal. So this gives us a lower and an upper bound for each input dimension in the network. And then we propagate these bounds through the network to derive some output bounds for the network. Now, crucially, as the network contains nonlinear operations, these output bounds will necessarily be an approximation, an over-approximation of the true output bounds of the network. Now, if the area defined by these bounds is entirely contained within the area of what we consider to be safe, then we can conclude that the model is probably robust. Otherwise, we simply don't know, and we need to refine the approximation some way. I will talk about these ways later in the talk. To give a simple example for a classification tasks, if we found that the lower bound for the true class of the input is above the upper bounds for all the other classes, then we can conclude that the classification is provably robust. I do think I have a problem with my slides, Nikki. They're not shown entirely. Maybe just do this. Great. Okay, with this I will start discussing the formal verification approaches, and I will discuss string-bound propagation approaches of increasing complexity. I will start with interval propagation. This method simply propagates the bounds that we have in the input using interval arithmetic. So in this example, we have a simple network here, and we want to derive the bound for the output node. And this will simply be -1 times the upper bound of the first input plus 1 times the lower bound of the second input. And this will give us -2. So this will be the lower bound of the output. In a similar manner, we can derive the output bound, the upper bound, and whenever we encounter a ReLU function, we simply set the lower bound to 0. So this is super fast, but it uses significant over-approximations at the output layer. And the reason for this is that because the method does not account for dependencies between the nodes in the network. In particular, what it often does is that it assumes that an input node can have its lower and upper bound at the same time. An easy way to see this is by try subtracting a variable with itself. Using interval arithmetic, we will expect the result to be 0, right? But because the method takes the variable to equal its lower bound and upper bound at the same time, the result will not be 0. So the second method I will discuss tries to alleviate this issue by propagating symbolic bounds instead of concrete bounds. Particularly, it propagates linear equations. So it starts with assigning a variable to each of the input dimensions, and then propagates these variables through the network. Here, for example, we have that the lower bound equation for node x3 here will be -1 times x1 plus 1 times x2. In the same manner, we can derive an upper bound equation for the node. And whenever we encounter a ReLU function, we approximate the function, we linearly approximate the function. We approximate from below when we are computing the lower bound, as I show in these figures here, and from above when we are computing the upper bound. Now, at each layer, what we have with this method is that we are expressing the bounds for the layer as symbolic equations over variables of the input layer. And we can use the concrete bounds at the input to concretize these equations, and this will give us concrete bounds for the layer. And because exactly the equations are over variables of the input layer, the method guarantees that an input node will never attain its lower and upper bound at the same time. So it alleviates this issue that we had with interval propagation. And by doing so, it is more precise. However, it does not alleviate the issue completely. It may be still the case that for intermediate nodes, we have that they attain both their lower and upper bound equations at the same time. So the last method that I will discuss, it's an extension of this, which completely accounts for the dependencies between the nodes. This is called symbolic interval propagation with back substitution. And it does so by working in a backward instead of a forward manner. It specifically starts the computation from the layer for which you are computing the bounds. It expresses the bounds for the layer as linear equations over variables from the previous layer, and then it back substitutes the variables with linear equations over variables from the even previous layer, and so on until the input layer is reached. Then as standard, the bounding equations will be other variables from the input layer, which can be concretized to give us concrete bounds for the layer. Now, by accounting completely for the dependencies between the nodes, the method is much more precise than symbolic interval propagation, interval bound propagation, but it's far more expensive as well. And this is because the back substitution step that I discussed, it amounts to computing products of coefficient and weight matrices in a backward manner through the network. This is far more expensive than doing a simple forward pass of an input through the network. Now, if we were to compare these methods, they would look like this. This is not a precise comparison, it's something that I draw by hand. But what we have is that interval propagation is very fast, but very loose. It's so loose that it can struggle to analyze networks of even of hundreds of nodes. Symbolic interval propagation is slower, but more precise, but still it can struggle to analyze networks with even thousands of nodes. Symbolic interval propagation with back substitution is far more precise, but far more expensive computationally. The method can scale up to networks of millions of ReLU nodes, and we really need this precision of back substitution to be able to start addressing practical models. So what I'm going to discuss now are some ways which can make the method more efficient, but without sacrificing any of its precision. And I will start with what I call here hybrid propagation. And this is a very simple method which uses all of the propagation methods to make back substitution more efficient. What it specifically does is that it uses interval propagation, symbolic interval propagation, to derive bounds for the layer. And then it uses these bounds to determine the stability of the ReLU nodes. By determining the stability, then back substitution is run only for the astable nodes in a layer. We really need precise bounds only for the astable nodes so that we can derive tight linear approximations for the ReLU functions, which will later be used for computing the bounds in subsequent layers. And this simple trick helps a lot with the efficiency of back substitution. It what actually enables back substitution to scale to networks of millions of nodes. And we can leverage this observation on the fact that we need to compute bounds only for the astable nodes even further with dynamic back substitution. In this method, we begin in a similar manner by using symbolic interval propagation to determine the unstable nodes. And then we initiate the back substitution process. Now remember that at each step of the process, as we go backwards, we have backward symbolic equations over variables of a previous layer. Then at each step, we stop, and we use the forward symbolic interval propagations for that previous layer to fast propagate the backward equations to the input layer. This gives us bounds that are less precise than if we were to run back substitution all the way backward, but more precise than running forward symbolic propagation. So we have some bounds of intermediate precision, which we can use to determine further stable nodes in the layer and removing those nodes from the back substitution process. In that way, we are making the back substitution process more efficient dynamically while we are running the process backwards through the network. Okay, so these were the basis verification methods that I wanted to discuss. I think these are now the core components in any neural network verifier. But as I discussed at the beginning, this can be inconclusive. in the case the over-approximation is too loose, then we simply cannot conclude anything. And in that case, we need to refine the approximations. There are two main ways to do that. One is by splitting the input domain. This will give us smaller input domains for which we can run bound propagation for each one individually. Additionally, we can split a ReLU function into its two linear segments and then run bound propagation for each of the subdomains. And we continue on doing this until the overall approximation at the output becomes precise enough to enable us to conclude robustness or find a counterexample. And we have very efficient implementations of this branch and bound scheme, which can also be GPU accelerated, and they work really, really well in practice. One main disadvantage that they have is that they do not readily account for complex dependencies between the nodes. These are dependencies that one can use to refine, to tighten, if you like, even more the over-approximation on each of the branches. And so now I'm going to discuss a different verification method that does exactly this. And this is based on mixed integer linear programming. So a quick reminder, a mixed integer linear program is a feasibility program over a set of constraints that are over real valued and integer variables. Here I'll be considering only binary variables, which variables are used to encode the piecewise linearity of the ReLU function. Here you can see the MLP encoding. So a verification query can be encoded precisely as a mixed integer linear program. I will not go through the details of the coding. I will just point out that the coding uses the bounds for the input to the ReLU function, and the precise these bounds are, the tighter the encoding will be, and the more efficient the solver will run to solve the resulting MLP program. So it's always a good idea to run the bound propagation method that I discussed previously before doing the MLP encoding. Having done the coding, what we will have is that the verification problem, or if you like, the network will be robust if and only if the MLP program has no feasible solution. And we can use any modern MLP solver to determine this. Modern MLP solvers run really well. The way they work is by implementing typically branch and bound schemes, where the branching is performed on the binary variables encoding the ReLU functions. And of course, the more this creates a search page in the which search page is of exponential size in the number of ReLU nodes in the network. And this is what makes neural network verification a hard problem. It is, in fact, an NP-complete problem. Now, as I said, modern MLP solvers like Gurobi run remarkably well out of the box. But we can still improve their efficiency by explicitly capturing some dependencies between the nodes in the network. So what do I mean by a dependency here? We say that an unstable node, so an unstable node, remember, is a node that, given the input bounds, the bounds on its input can be in either of the two linear segments. So an unstable node is said to depend on another node. If whenever the one becomes stable, then the other has to be stable as well. I show a simple example here for two unstable nodes, Q and R here. So what we have here is a dependency where if node Q becomes inactive, so it operates on the left segment, so it always outputs 0, then node R has to be active. Now we can exploit this dependency to reduce the search space on the binary variables. In particular, if we say branch on the variable Q and go to the inactive branch, then we do not have to consider the inactive branch of variable R, right? Because we know the ReLU node R will be active in that case. And we can compute these dependencies between the nodes very efficiently using simple linear analysis, which uses the bounds that we computed from the bound propagation step. Then these dependencies can be added as MLP counts or constraints to the MLP program being solved, thereby reducing the search space and improving the efficiency of MLP solvers. Additionally, we showed that they can be used as an effective heuristic to divide the original MLP program into smaller MLP programs that can be solved more efficiently. So these were the verification methods that I wanted to discuss. I will be finishing the talk now, and I will briefly discuss a challenge problem that we did with Boeing for the purposes of the DARPA Assured Autonomy program. So here we have an aircraft pose estimation task where we use methods that analyze correspondences between 3D key points in the real world with their 2D projections. And these 2D coordinates are computed using neural networks, units in particular. So the networks take a simple image, and they output the key points in the image. And we wanted to reason about the robustness of the networks on different types of perturbations, starting with infinity normal perturbations. So these are white noise perturbations, which can be coded using infinity normals, which give us lower and upper bounds for each input dimension in the network, which we can then bound propagate with the method I discussed previously. We can reason additionally about photometric transformations encoding different lighting conditions. These transformations can be encoded as a fully connected layer, which can be prepended to the original network, and where we add a new input node encoding the intensity of the transformation. Then by having bounds on the intensity of the transformation, these we can again propagate using the bound propagation methods that I discussed. We can additionally reason about geometric transformations. We can reason about any sequence of geometric transformations by taking a convex relaxation of these nonlinear transformations. These convex relaxations will give us linear equations for the bounds for each input dimension, which we can again propagate from the network using bound propagation methods. Now, the verification roadmap that we followed in the analysis of these models, and I think this is a typical roadmap in neural network verification, starts with a very, very important step, which is model simplification and input size reduction. This is essential so that the models become more amenable to verification. And what we found by working on lots of challenge problems with different customers is that models can usually be simplified without having any significant performance drops. Having done the simplification, then we typically tune the verifier and devise performance enhancements for the network and perturbations in question. For instance, the dynamic back substitution method that I discussed is something that we devised within Safe Intelligence to be able to toggle resonance with photometric perturbations efficiently. Having done the tuning, we then analyze the models by testing the robustness of the models on each of the test points. This gives us what we call robust accuracy, which does not simply express as the accuracy of the model, but it expresses how robust the model it is in being accurate. And again, this is very different from testing, where testing can only give you an upper bound on robust accuracy. Formal verification can give you the exact robust accuracy. Venus is a formal verifier that we use. We are planning for an open source release of the tool later this year. Now, what we typically find in the models that we analyze is that they are indeed very brittle to realistic alterations of the input, particularly to white noise transformations. And typically the conclusion in safety critical applications at least is that the models are simply not fit for deployment. I'll be concluding the talk, and I'd like to briefly mention two important topics that I did not discuss today. The first one is certified learning. So a question that we often get after analyzing the model in terms of robustness is that, okay, the model is not robust and we found these counterexamples, then what do we do? And the answer to that is certified learning. So these are methods that use the output of the bound propagation step that I discussed in the learning objective. And the aim is to derive models that are provably robust. And they work much better than adversarial training. The second point that I would like to briefly mention is tree-based models. Decision trees have the same adversarial vulnerability as neural networks do, and we have different verification and certified learning methods for decision tree models. To conclude, neural network verification is a relatively new area of research. It started approximately in 2018. Since that, we have made significant progress. We are now at a point where we can start analyzing practical models. Scalability is still an issue, though, in the area, and I think the way forward to more verified AI is not simply by scaling verification methods, but also devising simpler models whenever possible. And with that, I conclude, and I'd like to thank you for listening.
Are there any questions?
I want to ask about the scalability of the state-of-the-art certified training methods. Well, because adversarial learning is also an alternative, right? So I just wonder in what occasions that we need to choose certified training and otherwise
So
adversarial training.
scalability of certified learning, it's much better than verification, because there we typically use the more efficient bound propagation method, which is internal bound propagation. So typically, certified learning scales much, much better than formal verification.
Mm-hmm. Okay. Yeah, thank you.
Thank you for the presentation. I saw one of the results in one of the last slides where you had 100% accuracy. Yes, there. You had a couple hundreds. Could you just explain like the kind of data that you used to maybe get to this value, this result? Because I would think maybe there were any form of issues like, let's say, overfitting or underfitting or something, because 100% could raise a series of questions.
So yes, so here what I report is the robustness of the model when the model gives the correct output, right? So if it gives the correct output, is it robust in giving that output, right? And as I said, what we typically find is that the models are indeed brittle to realistic alterations, but when the perturbation is very, very small, okay, you can have 100% robustness is what we find, right?
Okay, thank you.
I have a question. So, have you tried different types of architectures, and have you seen a difference in robustness between different types of architectures? So we see here some grayscale images, but I'm assuming these are through some VAT, but have you tried similar approaches with LLMs or multimodal LLMs, and have you seen any difference in robustness there?
Yeah, we always get a question on LLMs. The answer is no, we haven't played with LLMs yet.
Okay.
But from what I know, they do suffer from the same adversarial vulnerability. The perturbations there are different with the tokens and everything, but no, we haven't tried.
Okay. And then a follow-up to the previous question. I saw in one of your slides you had a CNN architecture shown. Do you see differences between transformer-based architectures and CNNs when it comes to robustness using this method?
So I cannot answer that. We haven't compared transformers and CNN architecture in terms of robustness.
Okay, thank you.
Thank you.
Yeah, thank you. Thank you for your presentation. I want to follow up on Nikki's question. So I think you mentioned the interval propagation, right? So I'm not sure if it's computational possible that if we try to derive a bond from the input to the output for a like convolutional neural network, because we have so many nodes. Sorry?
For if we try to derive a
Yeah, like to propagate from the beginning to the final layer. It is computationally extensive, right? You have so many nodes, and you have sometimes if you don't have ReLU, you have some other activation layers. Maybe it is not even possible to derive such a bond. Yeah. How do you deal with these conditions?
So I think it's computationally efficient, first of all, because you're basically deriving two input tensors, one for the lower bound and one for the upper bound through the network. You are doing some interval arithmetic, which is more computationally expensive, but I think it's still very efficient.
Okay.
Now, with respect to other activation functions, these will have to be approximated, right, when they are nonlinear. And as I discussed with the ReLU function, this can be done, but at the cost of inducing significant over-approximations, and at least when interval-bound propagation is used.
Okay. Is it possible that we end with a very loose bond, that like including all the output space, that the bond?
It is very possible that you end up with very loose bounds. In fact, the simplest method that I discussed, interval-bound propagation, will almost always give you very, very loose bounds.
It's like the whole space, kind of.
Yeah, it can. The over-approximation can grow really quickly with respect to a number of things. One is how big are the weighted sums in your network. So the bigger they are, the more over-approximation you have. What is the depth of the network? The greater the depth, the bigger the over-approximation.
Okay, okay, yeah.
Are there any other questions? Okay, if not, thank you very much.
Thank you.